I'll be presenting here about the MPC, the model predictive control for the slow orbit system that we developed in Max for a few years ago, and we've been maintaining, trying to keep up with it. So let's just go forward. So I'll explain a little bit about this project, but like I won't go farther into the orbit control. We have a lot of talks about that, and probably have a couple more until the end of the day. But I'll explain a little bit about the MPC, so I can explain the implementation that we did and the Tango device that we did, and I'll talk about the tests on the storage ring that we did and the challenges that we're facing now. Like this was developed actually a couple of years ago. I think it was presented, most of it was presented already in 2023. At the time, it was the master thesis of a couple of students that I was advising at the time. And now, after trying to deploy it into production a few times, we have some outcomes of that, right? So I won't explain a lot about the orbit feedback here, but the main thing that MPC there is trying to solve for us, we have like a PI controller that is making this low orbit control for us. But the main issue that we have there is that it's very easy for our actuators to saturate. They tend to, for several reasons, they tend to go to their maximum range and desaturate. And the operators on the machine side, they need to manually bring back down the currents on the actuators. And it's a little bit of a hassle, especially when it happens during the night, at 3 in the morning, and we don't have specialists to help them. So the idea with the MPC was having like a stricter constraints on the saturation levels of our actuators. So, how is the control system, like the control system for our both storage rings? They're more or less the same. Here we have like for the one section of the big ring, I guess. Yes. So we have like the control, the corrector magnets. They're controlled by I-test for supplies, and we have Tango devices connecting with them, and that's our interface to the hardware with our control system is Tango. And for sensors, and these are our actuators. For sensors, we have like the library. I don't know if many of you use libraries, but we have like the libraries as our BPMs there. Since we have like two rings, we have like a little bit of different scales of problems. In the big ring, we have like 200 actuators on one plane and 180 on the horizontal plane, while in the small ring, it's like a fraction of less than half of the actuators that we actually have. So the problem to solve the correction on the smaller ring is much easier than solve into the big ring, especially when we have calculation issues. And the same with the libraries. So our requirements, as I said, one, we have to solve the saturation for the slow and fast orb feedback control systems. And if that ever happens to they get saturated, we should have like a strategy to get it to not be saturated anymore. That should be easy. The BPM readout sometimes can be a little bit of a trick because for this when we read it from this low orbit feedback interface, it can have like a delay between what the slow orbit feedback is reading for the BPM readout and what the fast orbit feedback is actually doing is a little bit more in the future. So we have some uncertainties on the models when we create that. One of the things that I mentioned here is that we have to correct the saturation of the fast orb feedback as well, which means I think most of you know this issue is that they are working together, and we try to offload a little bit the load that the fast orbit feedback has using the slow orbit feedback. So the fast orbit feedback system can always work in the middle of the range. That's why several people here talk a lot about mid-ranging strategies, is to guarantee that the fast orbit feedback is working in the middle of its operational range. So, and last, the RF system can also be used to compensate a little bit of the energy dispersion there, and we can incorporate that into MPC controller. Kind of easy. That's not true, but you can incorporate that. So when you talk about model predictive control, what do we have? So we have like a model. In our case, in the case of the slow orbit feedback system, it is can be represented by a response matrix between the BPM readouts and the actuator currents. And we can, for the MPC, you can use the dynamic to predict the current step, and if of the current value, use that the current value of the actuators according to the values of the sensors that you're reading. And you can also predict a few steps ahead if your model, your response matrix, also have information about how your system behaves for future states. If you have a derivative, for instance, that explains your system. And you have, like, for each step, you have like optimizer. It will be any nonlinear optimizer that can solve the optimization problem that is defined by your model. Obviously, any optimization problem can also be defined with constraints. So what is our mathematical definition here? We have like as optimization problem, which the MPC solves, it's trying to minimize a cost function. And this cost function, it will incorporate the state errors. So like the difference between the expected position for your BPMs and like your golden orbit and the values that you're actually reading in the BPMs. It will have like the control signal, the value that your actuators are actually applying to your current in your actuators. And you have like your prediction horizon, how many steps ahead you can predict with your model, and it will depend on your model on how well your response matrix can define the current step and the future steps. And you have obviously the cost functions that will be the relation, that will be, in most cases, will be the importance of your readout of your sensors. It's the same. So this function, like explaining in an easy way what it means, this minimization function, like this first term will penalize like tracking errors. The second term of this minimization will penalize control signals. So the control signals needs to follow what is represented by your response matrix. And the third term of this equation will penalize the error that when you have like horizon, like a prediction horizon, it try to penalize errors that will happen in the future. And the model that you have will serve as a constraint for your cost function. The initial state was also a constraint of your cost function, and the maximum values of readout values of your sensors and for your actuators is also part of your constraints, and that's the important part for MAX4. That would be like the limiting the constraint, the value on our actuators. So our MPC design. So the MPC, in our case, it was quite straightforward. As I said, it was the work of 2 master students. Our main model uses mainly the response matrix between the actuators and the sensors and the BPMs, and it's like a simple response matrix there. So you do not have really many huge depth for prediction there. You don't have a long operational horizon in our case. the X, the readouts are the BPM sensors for the BPMs. The actuators are like the currents in our magnets. And we can also incorporate a little bit as an extra line and column in our model, the frequency relation between the, that can also use to reduce, in this case, we reduce the energy by adjusting the delta of the frequency. So hopefully it would work like that. And then in our case, like the optimization problem that I showed before, how like the MPC optimization problem in the previous slide, our model will be represented by that control function, like the control model up there. And the Q matrices, like these are basically the costs for the cost functions for the sensors. Basically, it will be the importance of the sensors. Not all BPMs have the same importance as the others because they are distributed around the ring and they have different functions. So you can actually attribute importance for different BPMs. So you can use this importance of BPMs as cost signals. And the same thing with the magnets. They are also distributed around the rings. They have different functions and they can have different cost functions. So and as I said, the maximum values of our actuators and sensors are also used as constraints. And specifically, we also want to limit the speed that our actuators can change. So the change in our the change of the delta in our actuators is also a constraint in the implementation that we did. So it will prevent kicks. We're talking about a little bit about mid-range, like the two talks before talking about that, and that's pretty much what we do also in Max 4. What we do there is that we change a little bit the reference of the fast orbit system. Let me just go there. We change a little bit of the reference of the fast orbit system, change a little bit the golden orbit, according to the error that the MPC is seeing. So it will change a little bit the reference according to the predicted orbit in the next step. So we try to make a small mid-ranging strategy there. And this, it doesn't have to have every iteration of the MPC controller. It only happens at 5 seconds to reduce any noise that can introduce there. So I will not focus a lot on the Tango device implementation. So, but we have the interface for it and the configuration for it and how it works, and we can see the values that are working there and can be configured. I'll also skip a little bit the state handling. I think it doesn't fit this things. So what I want to tell here about the test that we did in the ring. It does have an initial transient space that can have quite a kick. But after that, it's quite, it tends to be stable, more stable than the PI controller that we were using before. But even with that, the sensor constraints and the actuator constraints were not broken. So it reaches the objective that we had. And specifically for their 3 tests, we saw that after we turned on the fast orbit feedback, we did have an increase of our noise, but that happens specifically because it were testing cold beam, and the libraries don't really deal well with noise when we are testing with cold beam, which is like the lower energy than the nominal energy of the beam. And now the challenges that we're facing, like as I hinted before, like the RF adjustment doesn't work like that. We had to simplify a little bit how we handle RF adjustment to make that work. We haven't been able to test that perfectly, but we are working on that. Calculations for the 3GV, the big ring that has 200 devices for each plane, it can be a little bit slow. So we are working on optimizing the implementation because that can sometimes doesn't reach time constraints for the model. and it's harder for the operators to understand what's going on. So when anything goes wrong in anything of the ring, while we were trying to deploy the production, they said, oh, it must be the MPC, turn it off and turn on back the old controller that they had. So it has been kind of a battle to get that working. Mainly because they don't really understand how it works, and because with the previous controllers, they could just like manually change the values on the actuators when they're starting to saturate, and that doesn't sit well with the MPC because it's trying to predict the next step. So it's a challenge to make that work. In the case of the RF adjustment, we are trying to use a more simplified model for the correction. And the future work is to introduce like a longer prediction horizon, incorporating a more complex response matrix, and to incorporate a little bit more of other disturbances on the MPC controller so it can be more robust over time. It was delayed because of the performance issues that we're seeing for the G3GV rings and the frequency adjustment that we had to do this past year. That's it. Yes.
How do you connect your BPMs to the fast roaming feedback? Is that a dedicated link, or do you need to connect a network?
He knows better. Yes.
They have a
sorry, the question was how do we connect the BPMs to the fast stop feedback? So we use Libera. So is a commercial, is a box, and we have a GDX module that then we interconnect the BPMs together, right? And then the fast stop feedback runs in this module called GDX inside the Libera unit. This is SFP. Yeah, optical fiber is yeah.
Using the single like Argon is doing this, have a single algorithm to handle both of them at the same time, because the libraries will be done on hardware, the fast orbit feedbacks done on hardware, and then you do slow orbit feedback on software layer, on the control system, distributed control system layer. So they are literally split.
Many thanks. More questions?
Yeah, I was curious about. So you have the Q matrices in your cost function.
Yeah.
Wondering if you have like different units mixing the errors with the control inputs. Have you developed any strategy or any ideas for the tuning of these matrices?
So that's I'm not going to give an answer that you like, but that's like slow work with the physicists, like the accelerator physicists trying to tune it manually. We start from the original controller that we have like a PI controller that already have some matrices for gain, for response matrix, and for some costs that we already have there. And we start from there with our physicists, like with the accelerator physicists, and then we see how the system is behaving and try to tune around it. Unfortunately, we don't have like a great strategy for that.
Recipe for.
No, sorry.
I'm wondering that how often you measure the response matrix, and under what condition that you needed to update the response matrix?
So that's a very good question. It's not really us do it. It's like the accelerator scientists that do it. They do it quite often. Sometimes they have like dedicated campaigns to do that. I don't remember if every year. Before it was more common. We have like several times a year, but nowadays I think it has been like once a year. It's not really necessary to update them that often. The control is quite robust. So. But well, it does degenerate over time, especially when have interventions on the ring, like we change things there, or we introduce like a new bin line and you put a new insertion device on it, then we necessarily have to create a new one. So
Thank you. Follow-up question that have you tried that physicists can produce this response matrix from the simulation code, which means that you can use a physics model to compute this response matrix at need, but this is depend on that how the physics model match your real machine. I'm not sure. So have you considering this option?
Yes, that is a discussion that we are currently like the mesh and everything we have in Max4. They are simulated by the physicists, and I have been talking with them to try to get that from like a simulated model that they use, but it's not something that will move it well along. But it's a discussion that has been going on. But at the moment they are measuring it during like campaigns for the accelerator.
Okay. I think it's time to go to the what?
I just answer real quick. Maybe you said this, but is that the reason for model predictive control? Because the machine and the response matrix drift over time. What's your driver for this?
The main driver is actually like the yes, kind of, but we also have like uncertainties on the things on how the accelerator work. If we have like some other interference, like a thermal interference in the actuators or the magnets or anything like that, that's not easily described by the model or the specific response matrix that we have like this noise that this change that can happen over time that will change that will affect how like mainly how the control system work, and it will reflect very quickly on the fast order feedback. If, for instance, if you have something that's changing how like the temperature effect that's changing how the magnets work, the fast order feedback will see that and will try to compensate for that. So the slow order feedback in this sense what we'll try to do with this lower feedback is like to reduce this strain on the fast order feedback, and then MPC particularly is there to we want to have it there to prevent the saturation of both systems.